print these statement, execute this statement for the test value 3. So these are not yet completed. So before that only, again the function is called with the test value 3, and as a parameter 2 is passed. So again the function will go from and start will from the initially, that is if. So here the test value is 3. So in our parameter as 2 is passed, 3 minus 1. So again now the new value of test will be 2. Again similarly condition will be checked, 2 is less than 1, not satisfied. So it will go to else statement, and again cout will be done. So in output you will see here 2. Then again it will go to the next statement where again the function is called before completing the last two statements, cout and return. Again the statement 2 which is written in comment. Here again the function is called. For now the value will be passed. So value 1 will be 2, means 1. So the condition will be checked. If condition is not satisfied, then again go with the else and print 1. Now you have to listen here. It's the final step. So now the test value is 1, and in parameter 1 minus 1, that is 0 will be passed. And if condition will be satisfied, cause 0 is less than 1. So here the return means it will return. It will not execute again. So now you have to take care that what I have said, that the function where it is called, it will return, the control will return again to that state. So for test value 1, the state means the control goes to the statement 2 and call the function definition and completed a task. Okay, because its condition is satisfied and return is nothing. So now the control will go back because test value 1, it is satisfied the all definitions which are written in the function. Now it will jump back for the test value 2. Because in test value 2 and 3, we have not done the output execute the statement of cout, test, and return statement, the last two statements. Because before that only function was again was called in statement 2. So it will return back when the control will return back for the test 2 and test 3 in similar ways like for the test 1. So in output you will see 3, 2, 1 and 1, 2, 3. Because the when the control will come for test value 1, then the remaining task will be performed like these one, the last two lines, cout, test and return. So cout test, for test is goes to 1, it will cout 1 after completing 3 outputs, 3 to 1. Now again the value will be printed in output 1 and function will be returned. So here it is the complete function definition is executed for test value 2. Now it will same will be executed for 3. So 1, 3, 2, 1, 1, 2, 3. Now I will show you this with the help of flowchart. Please take the next slide. You will understand best with the flowchart. Yeah, please move to the next slide. Anjane, may move to the next slide. Yeah, okay. So see here, what I have said you the controls and how it goes from where it is called, and the two basic idea which I said you to remember, these will be executed in the recursion. So you have to take care of that. The first, which is function, is called from the function statement again and again, and the from the statement from where the function is called, the controls goes back from the to the that statement after executing the functions definitions. So see, starting from the test value 3. Initially, we had passed the test value 3, and we have given the output as a 3, and again the function was called. So see the second part, that is print fn3 calls print function 2. Means the here initially we have given the test value 3, and the value passed was test 2, which as you can see it is written calls print function with the parameter 2. So the second control jumps from there to again see the next dotted arrow, void print fn2, and again the control specified the conditions, means execute the definitions. Then again you see the blue dotted line goes for print fn2 calls print function 1. From that only the line print fn1. From here only the statement again controls calls the same function for test value 3. Then again calls means execute that function for test value 1 and satisfied the if condition. That is if I is less than 1, this is 1 less than, means 0 less than 1, calls test minus 1. So when the test was 1, so 1 minus 1 0. Condition check 0 less than 1, okay, return nothing. Now here no function is called again when the print function 1 calls print function with the parameter 0. So now here you have to see how the control goes back to the from the statement from where it was called. So the last with the parameter 0, it was called from the statement print fn0. So after completing the task for print fn0, the statement goes to there and again execute the third and fourth point, because it was left before only before executing third and fourth point. The function was called again in the second point in the last second diagram. So it executes the print and return statement for the test value 1. So an output again after 3 to 1, 1 is printed. Then again the control goes back from 4 to 3 in the second box to execute the remaining next last two lines for the test value 2. So the in output the printed value will be 2 after 3 to 1, 1, 2. Then again for the test value 3, because it was also called from the third point in the first box. So then again the value will be printed and return nothing. So the final value output in the will be 3, and the whole functions will be called and nothing will be remaining and the task will be completed. So Anjali, please move to the next slide. So I should show you the result with the theoretical part written. Anjali, please move to the next slide. Am I audible? Hello.
Yes, yes, Samarpratap. Yes, Samarpratap.
Yes.
Your friend responding accordingly.
Anjali, oh, Anjali, move to the next slide, please. Yeah. So what I've given the output 3 to 1, 1 to back the output portion. The previous slide, output portion. Yeah, this one. So what I have said, the output same, the 3 to 1, and again in the controls reverse back after executing when the first called and the control was going back. So the output was after 3 to 1, 1, 2, 3. It is in the stack form that is written in the this theoretical part. I will just read you in a little fast manner this theoretical part, because it is the same thing which I have explained. So I will read you in 1 second, in 30 seconds. So when print function with the parameter 3 is called from the main function, memory is allocated to print function 3 with the parameter and the local variable text is initialized to 3, and the statement 1 to 4 are pushed on the stack as shown in the blow diagram. So stack here, the stack means it's an arrangement like you can imagine of keeping three boxes in a vertical manner. Name each box is 1, 2, 3. So what you will do in the stack, that the principal follower is last in first out. So if you keep the box like 3, then again in the over 3, the box with the number 2 will be kept. Then over 2, the box number 1 will be kept. So in this vertical arrangement, you have first kept the third number box. So when you will take out the boxes again from the arrangement, so you will take out first one, then second number box, then third number box. So this is the stack arrangement with the last one, last in, first out. So this is only it is written. So it first prints 3 in statement 2 with print function parameter called, and the memory is allocated to print function with the parameter 2. And the local variable test is initialized to 2 and statement 1 to 4 are pushed in the stack. Okay, like 3 to 1. Then similarly, print function 2 calls print function 1, and print function 1 calls print function 0, and print function 0 goes to the if condition print function 1 are executed and it returns to the print function 2. Now here it is saying about the when the controls goes back to from where it was called after completing the function definition, and so on. So in the output value from 3 to 1 are printed and then 1 to 3 are printed and the memory stack has been shown. Okay. Now now this I have told you about the from the recursion method. So I will Anjani, please move to the next slide. Yeah. So here the topic is the iteration versus recursion. The part I have explained about the recursion calling function again. Now I will show a numerical with the both recursion and iteration. Iteration means for loops. In where will we do not call function again and again, we go the calling of variable, repetition of variable. So, and the question is about calculating a factorial. Okay. So normal if we calculate factorial in mathematics, it is of 5. If we want to calculate, then we will take it as 5 into 4 into 3 into 2. Now how we will check with the recursion and with the iteration, we will see in the next slide. So Anil, move to the next slide, please. Yeah. So factorial using recursion. The same which I have told you earlier. You have to take in mind that the function will be called again and again from their call statement, and after completing the task, the function will return to the its call statement to execute the part which was remained before means after the calling. So here you have to take the same. So start with the main function int main. Here n is the variable of which factorial we want to calculate. For example, take of n is equals to 5. Okay. So here you will see the statement written print in the that quotations factorial of something and n comma f of n. So print is used to print the statement if you want as it is and the values of the variable. So here the values in the output will be printed factorial of is the n which now you have to see the n comma f of n. So here n and f of n. So f of n here the function is called because its definition is written above, where you can see with the comment factorial function that is defined with int f parameter int n. So that function is called in the printf parameter. So the control will jump from fn to that function definition again and will perform the task which is given. So when f of 5 is passed, so the 5 is passed into the parameter of function definition int n. Now n contains 5. So if n is equals to 0 or n is equals to 1, return 1. But our we have taken 5, so this condition of if is not satisfied. So condition is not stopped. Then we will go to else, which is our recursive condition. Here recursive condition is that it is written n is 5 and we have passed the value. So you have to remember here n is 5. So when the control will come to else statement, so it will return 5 into f of 5 minus 1, that is 5 into f of 4. So you have to see here the return statement. Before completing the return statement, again f of 5 means again the f of function is called. So f of 5 minus 4 means 4 is again passed. Here the return statement is not executed. If you imagine if we have not written the function, then the return will be 5 into means if just replace if imagine that we have not written here in the return statement f of n minus 1, only written n is written. So if the n value will be 5, so 5 value will be written in the call statement, that is f of 5 where we have called in printf. So it will be directly print the output 5. But here again we have called n into 5 into f of 5 minus 1, that is f into 5 into 4. Means here again the function is called. So before executing totally the return statement and passing the value, the function is called. Then again it will jump to the initially the like previously. So it will start from previous condition. So that is 5 into f of 4. Then again n is equals to 4 if condition is not satisfied. So again the control will works like you can see in the diagram. The working it is explained. You will see it clearly. Like initially 5 into f of 4. So again the for f of 4 the control will jump to the function definition and it will internally replace like f 5 into 4 into f of 3 because n minus 1 is passed again and again. So for in the next step, the control will go like f of 3 will be replaced with 3 into f of 2 because if f of 3 is there, so n into n minus 1. So 3 into f of 3 minus 1, it is 2. And again for 2 the value will be called. So 2 into f of 1. So here f of 1 uh, where n is 1 in the last condition, the if condition will be satisfied, that is top condition. If n is equals to 0 or n is equals to 1, return 1. So when now this whole task is complete for f of 1 because here the function is not called. So when the control goes back from f of 1 to f of 2, so it will collect the values like 3 into 2 into 1 means 2 into f of 1, that is 2. So when the control goes back, it will complete the return statement for every values for 3 f of 3 for f of 4. So like it will means give the value for the return statement when going backwards, means completing the task which was assigned. So from the last we will start like the f of 2 will be replaced internally like 2 into f of 1, that is 2. Then f of 3 will be replaced like 3 into 2, that is 6. And 2 is the value of f of 2. So now f of 3 value is 6. So for when it will replace the value of f of 4, the control goes back. So 4 into 6, 24. Then when again it will goes back from where it was called. So 5 into 24, 120. And we will get the final result when the return statement will be executed, 5 into 24. So here the at last the return statement will be completed. 5 into 24, that is 120. And the value will be passed to the statement where it was called. So it was called in the printf statement n comma f of n. So f of n will be replaced like 120 and return 0. So in the output we will see 120. So this was using recursion. This can be a little bit tough for someone. So it is easy for the iteration too. So in next slide I will show you with the iteration for loop. Anjane, please move forward the slide. This was using recursion. Now I will show you with the iteration. Iteration means repetition. So here I will not call function again and again because sometimes factorial can be, as I have written the slide 2, recursion can be costly for large number and it can be confusing for many people. So with the simple variable also, yeah,
Can you skim through the slides really quickly because we don't have a lot of time?
yeah, it's the last one.
Okay.
So this is using the approach. So in for loop, what we did, we initialize the variable I, and we will take this till our condition is satisfied with the condition given in for loop. So again, you go with the main statement, then see out num okay 5. We are taking example. Then now directly jumps to the main definition, function definition. It will be short. So here the for part is the loop part. The iteration part is for I is equals to 2, where I initialize the variable as 2 and the conditions for which the loop will go is I less than equals to n. N is 5 we have taken and I plus plus. So I will tell you with the first value and similarly it will go so that it will not waste time. So for value if we check I is equals to 2. So I is equals to 2, okay. 2 is less than 5, okay. Then it will go to the inner statement that res is equals to res into I. Means res initially is 1. So res is equals to 1 into 2. So now the res variable has value 2 and the condition again will move like I plus plus. So next value will be I is equal to 3. Then again it will check if 3 less than 5, okay. Then res variable will be like initially res was 2 because from 1 it goes to 2. Now it will again be modified 2 into 3. So 3 into 6 and like this we will proceed and will get the same value 120 with the iteration 2. So it is simple with the iteration 2 cause not need to apply recursion everywhere. Okay. Please move to the next slide, Anjali. Yeah, this is using while loop. Nothing to understand much about it. You can use for loop too. So I'm skipping this slide. Okay. So this was about iteration and thank you. Now Vikas will take from you.
Okay, thank you, Samarth. Anjane, can you just skip to the 51st slide? No. Can you just skip to next slide? Yeah. Okay, good morning, everyone. This is Vikas. Today I'm going to take floating point representation. The term for floating point, as the name itself, you can understand, floating point means a decimal point whose location is not fixed, which is especially used in computers. So if you go for the mathematical definition of floating point, the term floating point refers to the fact that a number's radix point can be anywhere relative to the significant digits of the numbers. So usually floating point exists in the form of plus or minus significant into base to the power of plus or minus exponent. Here significant also called as mantissa. So you can see the example there. So one of the important thing that you have to remember is here base will decide the nature of the number. So if the base goes to 10, it will be decimal number. If the base is 2, it will be like binary number. In the examples, you can notice that in example 1, 0.9 into 10 to the power of minus 10. As the base is 10, it will be for a decimal number. And the second example 0.101 into 2 to the power minus 7. as the base is 2, it is a binary number. Okay. And then can you just move to the next slide? Hello. Hello. Okay. So the topic is why floating point is used. So in computer, it will be hard for it to represent very small, tiny numbers. Like here in the example, you can see it is very small, right? In example 1, 0.00005. It is very small, and you can see a very large number. So actually, it will take very large bits of information to represent these types of numbers, a large number and a very tiny number. So if we convert those numbers into floating points, like if you can see in the example 1, so 0.00005, it is represented as 0.5 into 10 to the power minus 10. So if we take 0.5 into 10 to the power minus 10, here the exponent 10, if we convert it into binary, it will goes to 5 numbers, right? It will take 5 bits of information, and 0.5, it will take 3 bits of information, and it will be easy to represent if we use floating numbers. So that's why you use floating point representation to these type of numbers. So before representation of floating point, there will be some rules to represent. So we have to normalize the number given. The first point will be the integer part must be 0. Whenever you write the floating point, the integer part must be 0. And second one is, if the floating point is like 0.d1, d2, d3, so on dn into b to the power of plus or minus exponent. So one thing you have to remember is d1 must be always greater than 0, and all di ranging from 2 to n must be greater than or equal to 0. In the example, you can see 0.1234 into 10 to the power of 4. As the integer part is 0, it doesn't represent floating point. And in the second is equal to 1.23 into 10 to the power 3. 1 is the integer, so it doesn't represent floating point. Anjali, can you just move to the next slide? Yeah. For representation of floating points, IEEE, which is IEEE, I hope you people all know the full form of IEEE, Institute for Electric and Electronic Engineers. So this association has given two methods to represent floating point. One is single precision, which takes 32 bits of information, and second one is double precision, which will take 64 bits. So I will tell you about single precision. So what you have to do is you have to draw one table consisting of 3 columns, which is having S. S refers to significant, E dash. So E dash is the biased exponent, sorry. So where 120 bias will be added to the actual exponent. And third one is mantissa. So if you see the column here, from 0 to 22 bits, a mantissa will occupied, and from 23rd to 30, bias exponent will be occupying, and 31 to significant. So if you have the floating point as plus or minus significant into base to the power plus or minus exponent, so here if the sign of the significant is positive, you have to take S as 0. If the sign of the significant is negative, you have to take S as 1. And then next slide, please. So in double precision, same. As the double precision takes 64, from 0 to 51, Mantissa will take 52 bits, and E dash. Here the bias will be 1024. From 52 to 62, bias exponent will take, and significant bit as usual. So I just want to explain you these two methods through one example. So Anjali, next slide, please. Yeah. So here the question is represent 1460.125 base 10 in single and double precision format. So you can see it is having base 10. So it is a decimal number. So we have to convert into binary. So I have converted it into binary. It will like 10110110100.001 base 2. So now we have to normalize the number. I have normalized the number by single precision. So here the sign before the significant is plus, right? So you have to take s is equal to 0. So the bias here the exponent is 10. So as the bias will be added, it comes to 137 to the base 10. So here 10 is a decimal number. You have to convert into binary. I have converted it. What you have to do is, so if m here mantissa is equal to 0110, right? So you have to count it whether it is taking 23 bits or not. So if it is not taking 23 bits, you have to simply put zeros to the right of the mantissa up to 23 to fulfill the 23 bits. And if the bias is not taking 8 bits of information, what you have to do is you have to put required number of zeros to the left of the exponent bias exponent. So I have written the representation of the floating number in the last table, you can see. Okay, I will go to the double precision. Anjali, next slide, please. Yeah, in double precision, you can take. Simply like the single precision only, what you have to do is, you have to put zeros to the mantissa up to 52 bits of information and biased exponent to 11. So here the biased exponent is having 11 bits of information and there is no need to add any zeros to it. But mantissa is only having some 11 numbers, so you have to add the required number of zeros. I hope you all understand how to represent floating system and
Yes, very good, Samar Pratap and Vikash Bhavmeta. And be precise, as we are all as a production engineer, why we need to learn about computers, computer architecture, and C++, and floating points. Be precise with your information. With the same team, Bhavya team.
okay, sir.
Sir, can we start now?
Just a minute. Can anyone respond? Be precise with your answer. As we are all a mechanical or production engineer, why we need to learn about computers in detail? Why we need to learn computer architecture? Why we need to learn C++, and why we need to learn about the floating numbers and all?
Designing of products and all these requires, I think, softwares and all. So in this, the coding can be worked.
Yes. We need to learn the things. The software which is related to us is which is developed by the production engineers. As we
Yes,
are
yes.
using AutoCAD or SolidWorks or Unigraphics or CATIA or ProE or ANSYS or any software that is built by our people. It is our responsibility to know such a platforms like whether it may be C++, or the fundamental ideas about computer architecture, or it may be a floating points. It is essential to have an idea to build a software. These are the things we need to know. Anyway, my appreciation, Samar and Vikash. Savarni, you can take your decision. Savarni, your team.
Yes, sir. Is it visible?
I think it's populating. Yes.
It's visible, yeah?
Yes, Savarni.
Yes.
Am I audible, right?
Yes.
Yeah. So, hi everyone. Good morning. This is Team 4. My teammates would be Shaboni, Rahul, Yashasvi, Varshita and Kaushik and Shrikant. Today we'll be speaking about condition numbers. Condition numbers is a very new topic to all of us in production engineering. So we've tried our level best to keep the content short, engaging, and crisp, and we expect you that, and we also expect that it will be interesting to you. And in case of any internet issues or white noise stuff, I like apologize beforehand, and please ask you to bear with it. So now Rahul would continue with the introduction to condition numbers.
Hello, hello everyone. Am I audible?
Yes,
Yes,
Hello,
you are. Yes, yes.
am I audible?
Yeah.
Okay, fine. Hello, good morning everyone. This is Rahul, and we have a topic on condition number, and I am going to represent here introduction of condition number. Uh, so, in the field of numerical analysis, the condition number of a function measures how much the output value of a function can change for a small change in the input argument. This is used to measure how sensitive a function is to change or error in the input, and how much error in the output result from an error in the input. So in the simple word, like if you have small change in input, then there should be a change in the output result. And condition number of a function measure how much output value of a function can change for a small change in input argument. So here, very frequently, one is solving the inverse problem given fx is equal to y. One is solving for x, and thus the condition number of the local inverse must be used. In linear regression, the condition number of a moment matrix. Here, moment matrix means like it is a kind of special square matrix whose row and column index monomial. So moment matrix can be used as a diagnostic of multicollinearity. Multicollinearity means like situation like in which two or more explanatory variable each is in multiple regression. 70, can you move next slide?
Yeah.
Okay. So the condition number is an application of the derivative and is formally defined as the value of the asymptotic worst case relative. So here asymptotic worst case means like it will having a longest running time performed by an algorithm for any given input size of n. So it's relative change in output for a relative change in input. So what I'm already told, the basic definition, the condition number of a function, measure how much the output value of a function can change for a small change in the input argument. So here he used the function is the solution of a problem and the arguments are the data in the problem. The condition number is frequently applied to question in linear algebra, in which case the derivative is straightforward, but the error could be in many different directions and is thus computed from the geometry of the matrix. More generally, the condition number can be defined for non-linear function in several variables. If you guys don't understand, don't worry. We have a separate topic on it, so just wait. Can you move to next slide? Hello?
Yeah, I did change the slide.
Okay, fine. So here, a problem with a low condition number is said to be while a problem with a condition number is said to be a ill condition. What does it mean? It means like so from previous definition, it's like well condition means for a small change in input, there is a small change in dependent variable, or you can say in your answer. And but in ill conditioned, for a small change in input, there is a large change in the answer or dependent variable. So that's the basic difference between well conditioned and ill conditioned. In non-mathematical terms, an ill-conditioned problem is one where, for a small change in the input, the independent variable or the right-hand side of an equation, there is a large change in the answer or dependent variable, what I already told there. This means that the correct solution answer to the equation become hard to find. The condition number is a property of a problem. Can we move to the next slide? Okay, fine. So as a rule of a thumb, if the condition number k to the k equal to 10 to the power k, then you may lose up to k digit of accuracy on top of what would be the loss to the numerical method due to the loss of precision from the arithmetic methods. However, the condition number does not give the exact value of the maximum inaccuracy that may occur in the algorithm. It generally just bound it with an estimate whose computed value depend on the choice of the norm to measure the inaccuracy. So what the already I will told the basic definition, like the condition number is only a measure that how much output value of a function can change for a small change in input argument. So that's it defined here. Can you move to next slide? So paired with the problem are any number of algorithms that can be used to solve the problem, that is calculate the solution. Some algorithms have a property called backward stability. Backward stability means like the property of a certain algorithm that accurate answer are returned for a well-conditioned problem, and the inaccuracy of the problem of the answer returned for ill-conditioned problem is proportional to the sensitivity. So backward stability means, so in general, a backward stable algorithm can be expected to accurately solve well-conditioned problems. Numerical analysis give the formula for the condition number of problems and identify known backward stable algorithm. So hope you guys have a basic idea about condition number. So what the basic idea of the condition number is just simply, I already told this in simple words. If you have a small change in input, then there should be a small change in your answer or your output result. And the condition number of a function is measured that how much our output value of a function can change for a small change in the input argument. So thank you for everyone. Listen. Uh, so that's enough for introduction of a condition number. Uh, Hello,
Yeah.
am I audible?
So, yeah.
Okay, fine. Thank you, everyone.
So, introduction to condition numbers, we now see how to code the condition numbers. But before we delve into coding, I'd like to introduce you guys with some condition numbers to condition number is, as you have already seen, that condition numbers are always calculated in matrices. So for the first property, for any matrix A, the condition number of A would be always greater than or equal to 1. For an identity matrix, the condition number of the identity matrix is always 1. For any matrix A and scalar quantity gamma, the condition number of function of gamma and A would be the condition number of matrix A. And the last property being, for any diagonal matrix D, we'd be quoting it to a function diag with parenthesis di, and the condition number for D would be maximum of determinant of di divided by minimum of determinant of di. So if you're clear with all of this, we jump into the coding part of the condition numbers. So in this coding part, we do it through the language Python. We choose Python because Python already has a lot of defined libraries which would help us to use the already defined functions, and we can calculate it quite easily through that. And the library which we use it for calculating the condition numbers would be NumPy. So in today's presentation, we'd use the condition function, which is read as COND parentheses of the NumPy package to calculate the condition number for the given matrix. The COND or the condition function is of the linear algebra module in NumPy package. So the syntax goes as follows in the highlighted text box: numpy dot linalg dot cond, and the parentheses would be x, which is the matrix, and p equals to none. And here linalg indicates the linear algebra module, the cond indicates the function, and the numpy indicates the package. So let's view a few examples. Very first example would be calculating the condition number for a 2 by 2 matrix. So firstly, we have to import the library. For that, the step would be import numpy as np. The name np is a variable and can be changed as in how the user wishes to. And then we have to create a 2 cross 2 matrix. For creating a 2 by 2 matrix, we have to input the matrix. So for that, we use a matrix variable. Again, the variable name can be as in how the user wishes it to be, equals to np, which is basically the package imported, dot array. Array is the function we use, and in the parentheses, we input the matrix which we want to. right? So here the example is 4, 2, 3, 1. And then the next step would be printing of the original matrix. We do this to have a reference for the final output. So we print the matrix variable, and then for the calculation we store it in a result variable. The name of the variable again can be changed by the user, which is equal to np.linalg.condition parentheses matrix. This syntax is same as the one in which we had seen in the previous slide, and ultimately we print the result. So for the output, we move to the next slide. I hope all you guys can see the output, and this is the original matrix which we printed in the initial part of the program, and this is the condition number of the matrix, which is our final output. The new line text boxes can also be changed by the user if he wishes to. The second example goes on in which we have to find the condition number of a 3x3 matrix. This program is extremely similar to the first one, except for the input part, in which we basically change the 2x2 matrix to a 3x3 matrix. So let's run through it. The first step again being importing numpy as np. Then we create a 3x3 matrix. We name the variable as matrix equals to np.array, and then we input our array. The example here being 4, 2, 0, 3, 1, 2, and 1, 6, 4. And then we print the original matrix using the matrix variable, print parentheses matrix, and finally we store the output in the result variable as np.linalg.condition parentheses matrix, and finally condition number of the matrix. And as you guys can again see the output, the original matrix is through the first part of the program, and the condition number of the matrix is through the second part of the program. And now we'll move to a final example, which is going to be finding the condition of 4 cross matrix. The first and the second program, the difference in the second and the third program is also same. We just change the input, which is the entering the matrix. So it's the first line being import numpy as np. Then we create the 4x4 matrix as matrix equals to np.array, and then again input our matrix. The example here being 4, 1, 4, 2, 3, 1, 2, 0, 3, 5, 7, 1, and 0, 6, 8, 4. And then we print the original matrix for a reference, and we store the output in the variable result as np.linalg.cond matrix in parentheses, and we print the result at the end. The output here is similar to the first two. We print the original matrix first and through the initial part of the program, and then the condition number of the matrix in the second part of the program. We'll be presenting the slides to you later on, so you can just run these codes on your browser and see if it works or not. We'd be happy to take up all the doubts even after the presentation ends. And now Yashasvi would be continuing about the non-linear functions of condition numbers. Thank you.
Good morning, everyone. This is Yashasvi. Now I'm going to brief about the condition number for nonlinear functions. Condition number for nonlinear functions can be computed using calculus, as said by Rahul before. The condition number varies with a point. In some cases, one can use the maximum condition number over the domain of the function, while in other cases, the condition number at a particular point is considered. Next slide. Now, coming to the function in one variable, the relative condition number of a differentiable function f in one variable as a function is modulus of x f dash upon f. If it is evaluated at a point, modulus of x into f dash of x upon f of x. Derivation of this formula can be explained in next slide. And also we can remember this formula as the ratio of logarithmic derivative of f and the logarithmic derivative of x. This will also yield the same formula. This is because the logarithmic derivative is the infinitesimal rate of change of function. Next slide, please. Yes. From the basic definition of the condition number, it is the equal condition number is equal to the ratio of relative change in function f of x to the relative change in x. So here let us consider a small change delta x in independent variable x. Then the relative change in x will be delta x by x, while the relative change in f of x is f of x plus delta x minus f of x upon f of x. Taking the ratio, we will get x upon f of x all multiplied by f of x plus delta x minus f of x divided by delta x. The last term is the difference coefficient, and taking the limit is derivative, which we have seen in the last slide. This is the condition number formula for one variable function. Next slide. Here is the question that is what happens if the function value at a particular point x is 0? What about the condition number? The condition number will become infinite. What it means that for infinitesimal changes in the input can change the output from 0 to positive or negative. Hence, infinite relative change occurs. Condition number of some common elementary functions. I have tabulated some common elementary functions condition numbers in the next slides. Next slide. Condition number for this
Yes,
basic functions can be.
Marikant, just a minute. Today we'll complete the presentation with Marikanti's slide. The others can present tomorrow. Is it okay? Or
Yes, sir, fine.
yes, yes. You go.
So try to
Yes.
solve this.
We can mind.
Con-
Yes. Yes. Go.
Try to solve condition number for this basic functions. It is really easy. You can use the formula to find the condition number for this function, as everyone knows derivatives. Next slide. It's similar functions only. Next slide. Here is one example. F of x is equal to root x. Finding the condition number of f at particular point x is from the formula we seen before. The relative condition number can be find out. We will get k is equal to half. That is very small number. So we can say that the function f of x is well conditioned. Coming to absolute condition number, it is nothing but derivative of the function at a point x. So we will get k is equal to half root x. This is about condition number of one variable. Condition numbers of nonlinear functions in several variables will be explained by Varshita. Thank you.
Yes.
Sir, can I continue? Shall I start tomorrow?
For others, it is okay. We can continue, Sabarni. But I think you have the classes during 11:30. Is it so?
Yes, sir, we do have a class at 11:30.
Yes. Then we will continue tomorrow.
Okay,
I
sir.
appreciate to Sabarni, Rahul Arya, and Madhikanti Rashmi. Others we may take tomorrow 12:30. Sorry, 11:30. Thank you.
Okay.
We'll meet tomorrow.
Thank you, sir.
Yes. Nirmal, Nirmal. Nirmal is in presentation.